In this video, we are going to use the law of conservation of energy to analyze the motion of a dart in a crossbow. So here I have a crossbow, and as we found in the lab, the length of the crossbow stock is about 17 centimeters. And what we're going to do is we're going to, so this is the dotted line, so when I bring it all the way back, this distance here that I can pull back the string is 17 centimeters. I'm going to use a round number for the spring constant here, the strength of the crossbow, which is related to the metallic part here, of 100 newtons per meter, which is probably a little bit different than what you got in the lab, but I'll just use that round number here. And the mass of the dart, I'll say, is 10 grams. So our goal here is to determine the velocity of the dart using the law of conservation of energy. We've done this before using kinematics, but we'll see how this is done using the energy model. So first thing I'm going to do in the given is make sure all my quantities are in the correct units. So this is in grams. Our standard unit for mass is the kilogram, so I'm going to convert this to kilograms. So 1,000 grams is 1 kilogram, which is 0.01 kilograms. And then the distance here is 17 centimeters, so I'm going to make that meters. So 17 centimeters, there's 100 centimeters in every meter. 1 meter here. So this is 0.17 meters. And the goal here is to find the velocity of the dart as it leaves a crossbow. That's the goal. So we're going to use this information here in the law of conservation of energy to find that velocity. So the solution consists of 5 parts. The first step is to draw the reference line. The reference line is the point where we measure all potential energies from for gravity. Now in this case we're not going to be going up or down, so it's not going to play that much of a role, but when we deal with vertical motion it will. But nonetheless, I'm going to draw the reference line. I just draw it right here in the given with an RL. Step 2, I state the law of conservation of energy. I say energy at point A equals energy at point B. And that's more than stating that. I clearly identify which points that is on my diagram. So I'm going to analyze the motion from the fully cocked back position here at point A, so I'm going to label that as A, to where the crossbow string is uncompressed, point B. So I'm going to analyze this interval, A to B, right there. Okay. Step 3, draw the buckets. This is the most important part. This is the physics. If I can identify where the energy is for each of these points, then I can write the equation, and then it's a mathematical problem. So each of these buckets represents an energy. So at point A, the dart is not moving, so there's no kinetic. This dart is not above the reference line. It has no potential energy, so I don't fill in the bucket. But the bowstring is stretched back, so there is some potential energy due to a spring, so I put some energy in that bucket. At point B, the dart accelerates and it gains some speed, some velocity, so there is some kinetic. It is still on the reference line because I drew it right there on the crossbow stock. Again, in this problem it doesn't really make sense to have it, but when we do vertical type problems you'll see how that comes into play. And then the bowstring is fully decompressed, there's no potential due to spring. If we wanted to consider friction, we could use the drip pen here to account for any friction. The idea is that if I have some energy here, if it's a completely 100% efficient, no energy loss, the same amount of energy goes in this bucket. So I just pour the energy right in here. But if there's friction, I can model it as some energy being dropped in this drip pan, so if I spill it. But in this case, we'll neglect friction. So my conservation of energy becomes the potential energy of a spring, you know, is 1/2 kx squared, so kx squared at A equals 1/2 mvb squared, the velocity of B. So there's a 1-to-1 correspondence between the buckets and the equation. So that's your equation. Step 5 is just math, so now we just solve it using the given numbers. So I'm given 1/2 kxa squared is equal to 1/2 mvb squared, and all I need to do is solve for the velocity of B. So mathematically, the 1/2s can cancel. If I solve for VB, I have to take the kAx squared divide by m, and that's VB squared, so I need to take the square root of that to give me VB. Plugging in the numbers, I get, let's see here, 100, that's K. The XA is the 0.17, quantity squared, divided by the mass. Remember, it's in kilograms because I converted to kilograms, square root. And if you plug those numbers in and calculate the velocity, I get 17 meters per second, which is pretty close to what we got in the lab when we used the kinematics model. So, in summary, we can analyze motion using the conservation of law of conservation of energy. Step 1, we draw a reference line. Step 2, we write the conservation of energy equation. We clearly identify point A and B. Step 3, we draw the buckets and we fill in the buckets with the appropriate amount of energy for each type, kinetic, potential due to gravity, or potential due to spring, from the beginning and the end. From that, each of the buckets corresponds to an equation, either for kinetic or potential, and then step 5 is math. So we solve for the appropriate variable. So there's an example of the law of conservation of energy and the crossbow.